Oh, well, and it's not now. It treats it
Somebody called me.
possibility.
Cleaning out your office to the two desks, 3 computers, 5 words. "31 years I've been here, the director's office. Moved my office 5 times. Well, yes, I no longer have the connection collection of I no longer have any 9-track tapes.
Okay, welcome everyone for the last ITC lunch of the spring semester. You can tell that the spring is here based on the flowers that are blossoming outside. There is another indicator. We will have a conference celebrating 20 years for the ITC next week, exactly. So we will not hold the meeting here. In fact, there will be an ITC lunch as part of the program that will feature people who join the conference. And it will all be held in a nearby library, and we very much hope that you can join us for that, and the banquet that will feature Stephen Wolfram, and for all the talks of previous ITC members. And so that, I hope that anyone interested already registered. We will also have a nice event after the lunch today to acknowledge those who contributed for the success of the academic year. So please stick around, you'll get champagne, if you can tolerate that in the middle of the day. At 1:30. So at the end of this lunch, stick around, you'll have cookies. Those that don't want alcohol can have cookies. And also I wanted to mention we have a former ITC member who is now on the faculty at Purdue. His name is Paul Duffel, who is sitting right there. And we haven't seen him since the pandemic started. In fact, he got interviewed for the position he has just before they stopped shaking hands. Right? So, but you met in person with the selection committee, and then he was offered the position. And now he has his own students. In fact, one of them graduates next week. So we are very glad to see Paul, and that's an example for the kinds of accomplishments that we are proud of. Many of the most prominent astrophysicists that you know about went through our corridor, something that you don't know about. You might, if you come next week, you will see some of them. Not all. It's maybe, I would say, 20% of the people that pass through the ITC corridor and pass through there. So we have something to be proud of. Many of the people that joined the ITC late, recently, are not aware of the history. Some of us, including Ramesh and Eric at the end of that table, and Charles, know the... And Lars, but he's not here. What? Yeah, I'm looking around to see who else was around at that time. Anyway, so we are all grateful, and one of the reasons to be happy and as the spring starts. So please join us next week. And today, we have another reason to celebrate, and that is the Quito Award was decided by the senior members of the ITC a week ago to be given to the first two presenters, students who did exceptionally well in their PhD thesis, and we will hear a few remarks about what the thesis contains from the two of them. One is Andrew Saydjari, who will tell us about the statistical models of the spatial, kinematic, and chemical complexity of dust. And the second by Magda Siwek. Where is Magda? Who will tell us about the binary evolution in circumbinary disks. And we will not give them the prize today. It will be given at the banquet in a week. Indeed, that will be a much more festive event than we had, so we are very fortunate. And I wanted to thank, in particular, Eric Quito for establishing this award, and that was actually the fastest donation and fundraising campaign that I was involved in ever, because we just came up with the idea during a senior faculty meeting, and at the end of it, Eric's offered his generous donations. Aside from his many important scientific contributions, Eric is also very generous to the ITC. So thank you, Eric. We'll start with Andrew and then Magda.
Okay, well, thanks, Avi, and thanks, Eric, for endowing the award, as well as the selection committee for the honor. I'll just tell you briefly a quick overview of my thesis, which focused on developing statistical models to better understand dust in the interstellar medium, specifically where it is, how it's moving, and what it's made of. And so this talk will focus on the kinematics. I just wanted to give you a flavor of some of the work that we did to improve three-dimensional dust maps. Here I'm flashing back and forth between the sort of oldest version, or the next best version, and then the one that we created, which is labeled DCAPS here. And you can see the much improved angular resolution of the 3D dust map that we're able to achieve by improving our methodology and the deep photometric catalog that we used. And then on the far right here, I'm showing a high-quality near-infrared spectrum of dust from apogee from around 15,000 to 17,000 angstroms. Okay, but I'll be focusing on the kinematics in the small little vignette, which is to say that classically we have measured large-scale kinematics of our galaxy using gas measurements, something like H1 or CO. And in that case, you only have two positions on the sky and the velocity along the line of sight, and you have no idea where that gas actually is. And so you generally make these velocity versus longitude plots, and you see some coherent substructures, and you might associate those with spiral arms. But to actually leverage and sort of patch on some distance information, which is shown here as a top-down view in galactocentric coordinates, we generally appeal to masers, where we have both velocity and distance information via parallax. And so you can see sort of 200 of those plotted both in galactocentric coordinates here on the left and some points on the right that can tie these spiral arm models together. But the problem is there are sort of fairly few of them, and wouldn't it be great if we just had a kinematic tracer that contained distance information itself? And so that's what diffuse interstellar bands, or DIBs, can bring. And so the way that this works is you have some stars at slightly different distances and some dust clouds. And light coming from that star passes through a cloud and obtains an absorption feature on top of it, this diffuse interstellar band. And if that cloud is moving away from us, the wavelength of that feature is redshifted. If you have a star on the bottom right here, you would get a feature at the rest frame wavelength and one that's velocity shifted. And ideally, you'd be able to separate those kinematically. In reality, these features are fairly broad. They're about 30 kilometers per second wide. And so you just really get one wide Gaussian with its center wavelength as a dust-weighted average of these two velocities. And the story repeats for this third star. And so in total, by having many stars at different distances with a partial distance information given by the upper bound of the distance of the star, the line of sights probe different combinations of clouds, and you can reconstruct this in 3 dimensions and painting on the velocities of the 3D dust. And this idea is not new. It was really pioneered by Zazowski and Turner-Schwab-Peak and Zazowski early on. But these catalogs used fairly small numbers of detections of diffuse interstellar bands and really suffered from large systematics associated with stellar residuals and skyline residuals that we have solved. And so one of the main data products of my thesis is showing that we can clearly detect spiral arms in diffuse interstellar bands for the first time. This is 150,000 DIB detections in apogee of the 15,272 angstrom diffuse interstellar band. And that's what you're seeing on the left here as a velocity longitude plot. And on the right, you're seeing in galactocentric coordinates the distance to the background star that we're using to measure the diffuse interstellar band, just showing you that partial distance information. And if you look at the kinematic structure, you see features associated with our 2 nearest spiral arms, the local and Sagittarius Carina arm. But you see clear kinematics that are inconsistent with those velocities. For example, a lot of that is explained by the Scutum Centaurus arm. This is clear evidence that we're not only seeing our nearest neighbor arms, but looking through it to our next nearest neighbor, which I think is pretty exciting and something you can only do in the near infrared, like apogee. And you also see kinematic substructure associated with local spurs, like the Aquila Rift. And looking towards the outer galaxy, it would be easy to see something like Perseus or the outer arm, really exactly at the galactic anticenter. That's exactly where these velocities pile up, so it's not clearly distinguished based on this velocity plot. That's precisely why we need the distance information that DIBs bring. But slightly off the galactic anticenter, you see this spreading. This is exactly what you'd expect if you have detections from the local arm and the Perseus arm, this velocity averaging that I mentioned earlier. And so I'll just end by leaving you with this GIF flashing back and forth between the version of this plot that we've had in 12CO for a long time, that's all over the walls of the CFA, and the new measurement here in diffuse interstellar bands. You can see all the little substructure, like this little kink, and overdensities, as well as this underdensity in the center just left of the galactic center there. I just wanted to comment that there's one main difference between these 2 plots, which is this diagonal feature here in the DIBs that is slightly offset relative to the CO. It's not clear why, but this is exactly where we don't have very many masers locking down our model of Sagittarius Carina arms. I think it's going to be an exciting place to look at in the future. Thanks.
Just one quick question. What was the thing that surprised you the most that you didn't expect before your PhD and that you realized?
How bad our models of the atmosphere are.
You mean the Earth terms?
Yeah.
Really?
Yeah. Really. Those contaminations are pretty serious and they lead to bad systematics. That's why diffuse interstellar bands haven't been used for this for a long time. There were statistical sort of systematic biases on the order of 50 to 100 kilometers per second from stellar and atmospheric line residuals.
And is it because there is no commercial use for that knowledge?
I don't know. I mean, I think as astronomers, we often don't spend a lot of time thinking about our atmosphere and refining the models and also marginalizing over them correctly. We generally just try to divide by some approximate model or some rough estimate to get to the stellar information and just mask those lines. But you can't mask everything, and there are always fainter and fainter lines that start to matter and reaches the spectrum. And you just don't want to throw away the whole spectrum, but you have to make some compromise. Yeah.
Okay, so now they will quote you in the future.
Maybe.
The standard.
Maybe. Thank you.
That's all you hold.
Can you hear me? Yes. All good? Okay, hi everyone. So today I want to show what I consider the highlight of my thesis, which is a comprehensive model of binary evolution in circumbinary disks. So we know that binary systems exist on a variety of scales, and there are processes that allow them to form circumbinary accretion disks around themselves. But the difference between a circumbinary accretion disk and a normal accretion disk is that the binary actually exerts torques on the gas that stop the gas from flowing all the way towards the binary and sort of creates a cavity and a very asymmetric gas structure around the binary system. And so the question we are asking is, how does this gas affect the orbital evolution of the binary? And so to answer this question, we run a large parameter study over mass ratio. Where's the pointer? Oh, okay. Over mass ratio and eccentricity to study the orbital evolution of binaries in these disk-like structures. And so what that yielded was a model that tells us about the rate of change of the mass ratio due to accretion, the semi-major axis, and the eccentricity of the binary system. And in order to do so, what we do is we record the accretion rates onto the primary and the secondary, as well as calculating the gravitational interaction between the gas and the binary components to give us these last two quantities. And the neat thing about these results is that we can really summarize them in a single plot, which I showed yesterday during my thesis talk. If you were there, enjoy. So this is telling us about the eccentricity versus mass ratio distribution of just a synthesized population of binary systems. And what I've done here is I've plotted the semi-major axis evolution in this color plot here. So blue tells us the regimes in the parameter space where the binary will shrink or inspiral, whereas red tells us about the regimes in the space where the binary will outspiral or expand. And the streamlines tell us about the change in the eccentricity and the mass ratio of the binary system as it's evolving in the circumbinary disk. So then if I allow this simulation to run, you can see that the binary systems move along the streamlines and move towards the center of the plot. And this is a pretty fast process. It happens within just a few mega years. And you can see that we move from a really randomly distributed population to a very neat 1D relationship between eccentricity and mass ratio. So from knowing basically nothing about the parameters, about the orbital parameters of the binary systems, the circumbinary disk essentially organizes the binary parameters in this very distinct way. And so there are many applications for this. These simulations were run in hydrodynamics only. So we can apply the results to both binary star formation, where we expect that remnants of the disk from which the binary star formed might leave a circumbinary disk-like structure behind. We also can think about binaries that are evolved and may still have gas around them. The main application in my thesis has been to apply these results from the simulations to binary supermassive black holes, and that has implications for LSST as well as the nanograph results, which I'm a part of. And then I'm sure you can think of other binary systems that you might want to apply this to. So if you're interested in these models and you would like to use them in your research, please come and speak to me. I'd love to share the data I have. Thank you.
One of the things mentioned in the literature before your thesis was that the existence of gas would accelerate the merging of the binary black holes and therefore reduce the gravitational wave background rather than enhance it, because they spend less time orbiting each other if they were left to gravitational wave emission on its own. And so is that your conclusion as well, that generically in the universe we get less gravitational wave background because of that?
So actually we found the opposite. I'm going to show this plot again. So as you can see, we find these regimes where the binary can outspiral as well as inspiral. And it turns out if you allow this to evolve naturally, if you synthesize a population of massive black hole binaries and you apply these evolution rates to the binaries, allowing the opportunity for the binary to outspiral will actually enhance the gravitational wave background. So circumbinary disks actually enhance the gravitational wave background rather than reducing the amplitude, which at first seems like a very counterintuitive result, but it actually is caused by just a slightly longer time scale which the binary can spend accreting and increasing its mass and mass ratio. So
this is very interesting, and perhaps it can explain the nanograph result. It was a bit larger than they expected.
yeah, so we looked into this, and I'm happy to speak more about this offline, but the component of the enhancement that is due to the binary expansion is very small. It's just a qualitative difference in the outcome that you would expect.
Thank you, Magda, and we will see you in a week again.
Yeah, thank you.
Thank you. So these were short talks, shorter than usual. We will hear more next week, and we have now 3 additional presenters. Joshua Lovell from the CFA, he's speaking now about the our planet-disk interactions warping the eccentric debris disk Fomalhaut, which is sort of related to what we just heard in some way. And then we'll hear from Ricardo Yarza from Santa Cruz, who will talk about planets engulfed by their host stars. And finally, from Rocio Kiman from Caltech, who will tell us about estimating M-dwarf ages based on Halpha and kinematics. Joshua, please.
I'm going to skip it. I'll wave my hands if I need to point it to me. Hi, hopefully everyone can hear me. I'm Josh. That's me. That's Fomalhaut, and I'm going to tell you about why I'm interested in that guy. So I'm an SMA fellow. I'm usually based across the road at 160, but when the carpets are being replaced, I'm a sort of vagrant around the corridors here, or I'll be squatting in various offices this week. Before I start, I wanted to highlight the contribution to this work by my various collaborators, but in particular, I wanted to highlight Elliot and Jay. Elliot is a collaborator of mine who's actually visiting next week. Elliot's a theorist, and his schedule's been sent out to you also. If you want to find a time to meet with him, please do. He's around all week next week. And this is Jay. Jay is a graduate student who did a lot of the ALMA imaging for the results that I'm going to present today. So I want to start by telling you all who Fomalhaut is, what I think is going on in this extremely interesting planetary system, and then I want to tell you about the next steps in my research. So let's start with this. That's Fomalhaut in the top left. It's one of the brightest stars in the sky. It's about 7 parsecs away, and it's an A-type star. Its name actually derives from the Arabic Fomalhaut, which means Al-Janubi. It's the mouth of the southern whale. It's in the Piscis Australis constellation. And what makes this star so interesting is the fact that it's got this very bright circumstellar disk around it. And this is a debris disk, okay? It's not a protoplanetary disk. The star is way, way too old for that. It's about 400 million years old. But the way you get these disks is through collisional replenishment of the dust. So every time a planetesimal in an orbit collides with another one, it produces some dust and refills these rings that we see here with the JWST images. What's most interesting about this system, however, is that it's extremely asymmetric. If you try and plot the distance out from the star to the top of the ring versus the bottom of the ring, you see that you have to go a lot further before you hit the dust, okay? It has an eccentricity of about 13%, which is pretty high for as far as a debris disk is concerned. It's also got this peculiar asymmetry in that if you plot how much dust there is as a function of the width around the disk, it changes, okay? In the south of the disk, it's much wider. So it's close to the star, but broader. And at the top of the disk, it's further from the star, but narrower. And if you stare at this disk in different wavelengths of light, you see a completely different morphology. On the left, you've got the JWST images, and that's observing in infrared light, and you can see the south side of the disk, the main belt that is much brighter than the north. Whereas if you look at this object with ALMA, you see that the top of the ring, the apocenter, is brighter. And various explanations exist to explain why that might be the case. And they've often referred to as a pericenter glow or an apocenter glow. You can see these references if you want to learn a little bit more about those. What I'm most interested in, how did they get there? Why is it that this structure looks exactly like this? And there's some nice ideas that exist, right, that can explain these types of morphologies with planet-disk interactions. And these are based on some secular restricted three-body dynamics, which I'm sure plenty of people here know way better than I do. But effectively, if you have a planet that's inside the region of a planetesimal disk or just some outer body, and there's a star there as well, you can drive an eccentricity through that disk, okay? You can drive an eccentricity outwards as a function of the planetary properties, the eccentricity in semi-major axes, and how far away it is. The opposite actually happens if a planet's outside of a disk, but we don't need to worry about that too much today. I think the most important thing I want to say is when you have an eccentric planet inside the orbit of some third body, that planet can drive its own structure into that disk. Okay? It's really, really nice in planet-disk interaction studies when you have a planet. Okay? About 10 years ago, sorry, no, 10 years ago, longer ago than that, about 2008, Fomalhaut B was reported, okay? And that's a planet that sits right on the inner edge of this disk, and it's like, great, we've got something that we can point at and say that's what's causing this structure. And yet, when Hubble went back and looked at this system several times afterwards, it found that this object was fading. It also had non-orbital motion. It's just like some dust cloud, okay? In fact, NASA's Exoplanet Archive has delisted this. Take that to one side for now. I want to try and convince you in the remaining 5 minutes that I still think there must be some sort of body in this system to give us this structure that we see here, okay? This is the latest ARMA data that's available for Fomalhaut. It's extremely high resolution. It basically doesn't get better than this for debris disks at millimeter wavelengths. This is like 3 to 5 AU resolution given how close the system is. And you can see again that extremely sharp brightness asymmetry is present. I want to argue that there's an effect going on in this disk that me and Elliot have termed eccentric velocity divergence. And that is, take the system that I just described of a single orbit on the outside of a planetary perturbation and extend that into a system where you have concentric rings, i.e. concentric planetesimals. What you end up with is a situation where the eccentricity distribution, which you can see on the very left-hand side there, falls as 1 over A. What does that system then look like if you plot those concentric rings? Well, it looks like that. The opposite happens if you have something that's rising with semi-major axes, okay? And as I said, that's sort of an internal planet-like scenario, that's an external planet-like scenario. And what I hope you can see is orbits bunch up, right? If you were to have a slightly unresolved situation, you would see more mass in this region of the disk versus the same region on the other side and vice versa. So what I've been looking at recently is what happens if we try and parameterize this in a slightly different way whereby we can investigate what happens between these scenarios. And these are various models that I've made which actually use the parameters of Fomalhaut. And you can see what happens as you go from a positive to an increasingly negative gradient, something that's more planet-like on this right-hand side. The apocenter of the disk at the top starts to narrow and gets brighter. The pericenter broadens and gets fainter. Okay? That's the exact same situation that we see in the disk of Fomalhaut. So that begs the question, can Fomalhaut's disk be shaped by some planet-driven eccentric velocity divergence? And I think this is fantastic evidence to say yes. And the reason I think that is that this is what happens if you let MC run until it's converged using a best fit model finding solution with the models that I've made, and you take that away from the ARMA data. You're left with a structure which is not there, okay? It can be almost completely explained by a very simple model fit. And I want to emphasize that the model fitting that I've been doing is incredibly simple. And what's most interesting is the result finds that you do indeed need something that's very negative. You need something that's certainly less than -1, about -1.7. And this is really cool because that highlights the fact that there does need to be some sort of body in this system that drives its structure in this way. Okay. I also want to say this is the first time this has been done, so I'm very, very excited and proud when we can finally get this submitted and published, I hope, because all of this is unpublished work at the moment. What can we learn about the possible planetary parameters of this system? Well, in order to drive the types of structure that we see to get the model parameter fits that I find, we need things that are in these ranges. Okay, you need a planet about 110 AU, needs to be fairly eccentric, and it needs to be pretty low mass. And that would actually explain the fact that it's not been seen with JWST or HST, but it can still cause these structures. The difficulty is it's very hard to see a planet like this, so we're going to have to wait for probably a few decades before we've got a chance to prove whether or not this is right or not. And I want to ask one more question if I just have time, and I think the time is probably about to go. But that is there something else going on as well? And I want to ask that question because everything I was saying earlier was based on planet-disk interactions where a gradient of -1 would be a simple planet perturbation. And what I'm finding is a gradient that's actually slightly steeper than that. So I've been discussing further with Antronik Safilian, who has actually just taken up a 51 PEG fellowship in Arizona, about the possibility that we've also got self-gravity interactions between the planet and the disk as well. What these can seek to do is enhance the steepness of these negative eccentricity profiles quite substantially, depending on the mass ratio between the disk and the planet. And the fact that we've got something that looks like it could plausibly be much steeper than minus 1, down at minus 1.7, might suggest even that we've got evidence that there is self-gravity at play in this disk and that it's relatively low mass because it doesn't need to steepen by too much. This is to be continued. This is work that I want to try and get wrapped up with Antrik in the next few weeks for this paper, but some of it we're planning to work on again in the future. So, you know, what have we obviously neglected in this study? Gravity, but maybe it's there, okay? And I think I've raced through this very quickly, but I'm going to leave my summary points here, and I'm happy to take any questions or, you know, have any thoughts from people if you have them. Thank you.
So, George, is it possible that the system was made or formed with this eccentricity? Why do we need a perturber?
You need.
Yeah. We do see eccentric disk, for example, in M31 around there.
Mm-hmm. So that's the other aspect that I didn't tell you about. Elliot and me have been working on rebound modeling to try and explain and understand when this structure could have formed. If you want a structure to form like this over 400 million years, gradually via secular interactions, then you do need a planet there. If you want to start out with an eccentric configuration, then you actually need a protoplanet in the system as it's forming to do so. You can actually find a solution that does that. That still requires a planet. Does that make sense? You need something early on in order to induce the eccentricity profile that we see.
As I mentioned, in M31, there is no binary companion to the black hole, and the disk is eccentric. But that's a disk of stars.
Sure.
And the question is, in principle, you can have a perturbation that caused it early on, and then it stayed imprinted on the debris disk. But anyway, remains to be seen.
It certainly does.
Any other comments or questions to Josh?
Why do you see the pericentric glow in infrared and the apocentric glow in millimeter? How does that relate to these orbital configurations, do you think?
So in the infrared, you're dominated by the thermal component of the dust.
Okay.
And so to first order,
So
whatever's
it's hotter when it's closer.
Yep. And then in the millimeter, you're more sensitive to the mass distribution. And therefore, if you have more bunching of dust up in various regions, you're more sensitive to that. So even though it's still colder up there, the mass configuration wins out.
So this is kind of the experiment you're doing. You definitely need to do it in the millimeter then, because you're tracing where the mass is in the orbit. So that's really cool.
Exactly. So in the infrared, you can see the width differentials, but you can't actually see whether or not there's sufficient bunching going on. I tried, and JWST deadline convinced me that actually it's not possible with JW. You can do it with armor.
Awesome. Go ahead.
Yeah, so wonderful. So is this any optical data as well, like regarding to, program question, what you see in quantum frequency?
In optical, this is what you see. So in the optical data, you're dominated by scattered light emission. So what you see here is the ring where the far left-hand side is just inclined towards our line of sight, so you get preferential forward scattering. You do as well see some differences in the widths, and you do see the fact that it's eccentric, but it's very hard to study what's going on here because the scattered light is really not so sensitive to the thermal dust emission that I'm studying.
Other questions? Oh, up there. Go ahead.
Yeah. Super cool. Just probably naive question. What are the chances of forming just one, I'd say fairly light planet so far out, and nothing in the middle?
I would say fairly low. Planet formation happens much more frequently and more easily much closer into the star. I find it hard to believe that there isn't some form of like giant planetary system in the inner regions. How do you get planets out at tens, hundreds of AU even, is an open question. How did Neptune get to its orbit? Well, it probably got scattered by some interaction earlier on between Saturn and Jupiter. So I don't think if there's a planet out there, it necessarily formed there. In fact, that could be one explanation as to how it became eccentric. It basically got a massive gravitational kick by an inner body. There's one idea. It doesn't necessarily need to form at these distances as long as it can find some way of getting there. That would require something inside as well.
Okay, let's thank Josh again.
Hi, my name is Ricardo, and I'm a grad student at UC Santa Cruz. I'm super excited to share today some of the work that I've been doing as a visitor at the CFA, focused on the engulfment of planets by their host stars. This is work that has immensely benefited from discussions and collaborations with people here, so I'm very, very thankful for that. And I'm also very thankful to everyone for welcoming me into your community. This figure shows a subset of the known exoplanets. Each point corresponds to a planet, and the radial coordinate of that point is the orbital separation between that planet and its host star. There's a lot of information in this plot, but what I want to highlight is that the red dots are the planets that, at some point during the main sequence or post-main sequence evolution of their host stars, they will be engulfed. And you can see that systems up to a few AU will be engulfed, so we expect that a lot of planets will eventually undergo this process. There are other lines of evidence that suggest that engulfment is relatively common, and one of them is the few percent or so of main sequence stars that have abnormal chemical abundances that are hard to reconcile with explanations other than the engulfment of a planet. And also the fact that main sequence stars that have hot Jupiters tend to be much younger than stars that don't have them, suggesting that tidal dissipation, which shrinks the orbits of these exoplanets, is efficient enough to get them engulfed during the main sequence. So we have multiple lines of evidence. The current architectures of planetary systems suggest that a lot of the planets that we know about will be engulfed, whereas observations of potential stars that have engulfed planets suggest that many planets have already been engulfed. And the connection between this past and future evidence came last year when a team of people, including several people at the CFA, discovered an infrared and optical transient that we think is the result of a star engulfing a planet. And this picture over here is showing one of the protagonists of the story. This little dot is a star that we think is roughly the mass of the sun and probably close to the main sequence, on the main sequence or just barely evolving, turning into a giant. And this picture is from the 2000s. And up in 2020, this star began brightening in the infrared, which is the red line that I'm showing here, over the course of a few hundred days. And then after brightening in the infrared, it started becoming brighter in the optical as well, and then subsequently faded over a timescale of a couple hundred days. And this brightening is very qualitatively similar to the brightening that we observe when two stars merge, but quantitatively, it's smaller by a factor of about 1,000, suggesting that an object that is much smaller, perhaps planetary sized, is responsible for the brightening. So if this brightening is the result of the engulfment of a planet, let's try to build a timeline of the sequence of events. This plot is showing a few useful timescales during the engulfment of a Jupiter-like planet by a star like the Sun that has evolved to be 2 solar radii in size. There are two vertical lines that I want to note here. The first one is showing the surface of the star, and the second one is showing the orbital separation at which the planet begins interacting with the stellar surface. And shown as colored lines are the timescales over which the planet's orbit is decaying as a result of either tidal decay, which is the orange line, or drag when the planet starts interacting with the surface of the star. And for comparison, here's the orbital period as a black line. So you can see that when the planet is outside the star, tides are slowly in the sense of on timescales much longer than the orbital period, bringing the planet inwards. And when the surface of the planet comes into contact with the star, drag takes over and starts being the dominant source of decay. And the planet is going around, being in contact with the star surface, grazing it over the course of many, many orbits until the timescale for the decay because of drag becomes comparable to the orbital period, at which point the planet just plunges into the stellar interior. And that happens approximately when the planet is like half immersed into the star. So here's kind of a qualitative picture of what I just described. We first have a planet that is skimming the stellar surface, grazing it, and perhaps yielding some sort of wind that is expanding and cooling and forming dust. And then a stage where the planet plunges in and deposits a ton of its orbital energy into the star over a timescale comparable to its orbital period. And to give you a sense of what this full engulfment place where the planet is inside the star looks like, here's a little diagram. The left half shows a star that has engulfed the planet, and the right half shows a 2D slice from a 3D hydro simulation of the part of the stellar envelope that is in the vicinity of an engulfed planet. And you can see that the planet is driving a shock, and it's restructuring the density field of the star around it, and experiencing drag forces that dissipate the kinetic energy of the planet and heat the star, and are ultimately responsible for the orbit of the planet decaying inside the star. So if we think we have this rough picture of what the time sequence of events is, the next step is to try to understand how they correspond to the parts of the light curve that we observe. And when we started looking at this, we wondered, can we use the tools and conceptual frameworks that already exist to model stellar mergers to model this planetary engulfment event? In other words, can we think of planetary engulfment events as a scaled-down version of stellar mergers? And when we try that, we run into some issues. One of the features that are common among stellar mergers is that when the stars merge, there's a really large amount of ejecta, and that ejecta expands by a couple of orders of magnitude before becoming transparent. So the photospheres that we observe in those events tend to be like 100 times larger than the star from which the ejecta came. But in this event, the photosphere that we observe is only a few times the radius of the star. The star is a few solar radii, and the radius of the photosphere is a few times that. And that's hard to reconcile with the idea that these events are powered by a large amount of ejecta close to the escape velocity. Because if the planet is ejecting material near the escape velocity, like we think happens in stellar mergers, then it would only take a few hours for that material to reach the observed photosphere at a few solar radii. But instead we see that the transient lasts of order 100 days. And even if you focus on the plateau near the optical peak, that's like 20 days or so, and it's still really hard to, for this fast-moving material to produce a transient with that duration. Another way of saying the same thing is that if we wanted the material to reach the observed photosphere over the observed characteristic timescale of the transient, which is like 100 days, it would have to be moving at about a few kilometers per second, which is a tiny fraction of the escape speed of the star. So perhaps the long-term behavior of the transient that we're looking at, the behavior that is responsible for the 100 days or so, is not ejecta radiating, but the result of a heated and extended star becoming brighter and larger, and then gradually returning back to its original state. So we can think of it as having two different limits of transients. We have the very large stellar mergers that eject a lot of mass and have huge photospheres. And on the other limit, you have dropping a pebble into the star and nothing happens. And then there's something like the planet in the middle, where the perturbation of the planet onto the star is significant, but the star is able to respond to a gentler adjustment of its internal structure rather than by losing a ton of mass. So here's kind of a schematic diagram of the light curve that I showed you earlier with the phases that I also showed earlier schematically and kind of where we think they could potentially fit. A lot of the work that we've been doing over the past month or so is trying to turn this qualitative picture into quantitative models of each of these phases that we can compare against the observed light curve. And I think completing that is part of what I want to accomplish in the couple of months that I have left at the CFA. And I'm really excited to share this work in progress because I think the feedback that you have would be extremely, extremely helpful. So if you're interested in this problem, please reach out to me. I'm really interested in what you have to say. Thank you.
So Ricardo, most of we know that the sun is not typical actually, that most of the stars, by almost a factor of 10, are dwarf stars. And the interesting question is, why was this the first event observed? And obviously, dwarf stars are much denser than the sun, up to 100 times denser, so they would tidally disrupt the star, a rocky planet passing close to them. And the appearance of this flare would look very different. Did you think about what happens near stars that are more typical?
Yeah, I think, so if you think of the fact that perhaps most hot Jupiters are destroyed during the main sequence, that would mean that they're probably tidally disrupted instead of fully engulfed because of the...
Right, exactly. So the process is quite different near most of the stars. They destroy the planet before it gets to the star.
Yeah.
Right.
And in this star, I think the pre-outburst dust models are consistent with a planet that is at least several Jupiter masses. So it's something that would probably make it would be able to reach inside the star.
In the case of a solar mass star, yes.
Yes.
But
yes.
if it was a dwarf star, it would never make it. Because it would destroy it tidally before it absorbs.
I think so. And I think it's super interesting to think about what the observational signatures of that would be, given that we expect a lot of planets to undergo that fate instead of this fully engulfed fate. But I don't know exactly what they would look like.
Go ahead, Eric.
I was just wondering about the source of the heat that causes the star to expand. So there's the mechanical energy, and then, but if the planet is made out of hydrogen, fresh hydrogen, interstellar hydrogen, would it have enough deuterium in it to significantly affect the star when it enters the outer part of the star and it starts burning deuterium?
Oh, you mean that the burning heating rate could be comparable to the mechanical heating rate?
I was kind of curious about that. But stars, when they're accreting, can puff up. Burning deuterium in the outer part of the star.
Yeah.
But it's not a whole lot of mass, is it?
Yeah. My intuition is that probably the mechanical heat from the planet, the energy that is being dissipated from the orbit dominates, but I haven't done a calculation explicitly.
And the planet evaporates quickly, right? It doesn't survive all the way to the core, does it?
Definitely. I think they definitely dissolve within the convective region, maybe like 10 or 20% of the radii of the star.
So it's not, maybe not hot enough.
Well, it could be. I mean, they can burn deuterium in the envelope, right? But not right in the core. It has to be hotter to burn hydrogen.
Any other comments? Thank you, Ricardo.
Thank you.
right, can everyone hear me? Hi everyone, my name is Rocio Kiman. I'm a postdoc at Caltech. Thank you very much for the invitation, and I'm here to talk to you about the lower masses that they were just mentioned. They are everywhere, they are very common, and we don't understand them. So let's start by saying that ages of low mass stars are very challenging to calculate. We have a lot of methods to estimate ages for higher mass stars, so I'm defining high mass stars as larger than 0.6 solar masses, but that's for me. So we have methods like isochron fitting, astrosesmology, gyrochronology, and empirical statistical age relations. But when we go to the M dwarfs, or low mass stars, this doesn't work. So isochron fitting, the luminosity temperature of M dwarfs change very slowly with time, so we cannot use isochrons to get a precise age. Astrosesmology, we haven't found pulsations on M dwarfs, though we're looking for them, so if you're interested in that, come to talk to me. And we don't have a gyrochronology relation for M dwarfs yet, or it looks like for some of the M dwarfs, we might not even get one at all. So we're stuck with empirical and statistical age relations if we want to try to get an age for this type of star. And for that, we need parameters that are related to age, calibrate those relations, and then using those parameters to estimate ages for the rest of the stars. And I'm going to talk to you about a few of the methods that I'm using to try to estimate ages for these M dwarfs. So one is kinematics. Kinematics, we can use it to get some sort of lower limit to the age, and I'm going to tell you why. So when a star is born close to the plane of the galaxy, so its vertical velocity, for example, vertical or radial velocity are going to be closer or smaller to the plane of the galaxy. As they get older, they would interact with other stars, and they spread out, and their velocity can increase. And so if we look at the orbits in this graph, so a young star would have an orbit similar to the yellow one, and an older star would have an orbit maybe closer, is exaggerated as the green one. So if we do this, the vertical velocity as a function of age, we see that that spread is going to increase with time. So if we measure a vertical velocity, we can say that that star is not going to be younger than a certain age, but it could be older. So that's why I'm saying like it could give you a lower limit to the age and an approximate distribution probability. Another way, and I always like to say this because thanks to Gaia is that we can use this as an age indicator right now. Gaia is providing us amazing parallax, proper motions, radial velocities, and that is allowing us to use this technique to thousands of stars. The other thing that Gaia is allowing us, and the other way to get ages from kinematics, is using companions. One, for example, is using a binary. So if you have an M dwarf co-moving with another star that you can get an age for, you can assume that both stars were born at the same time and extrapolate the age of that main sequence to the M dwarf, to the age of whatever star that you have, and give it that age to the M dwarf. And the other method is moving groups. So Gaia has been allowing us to find the new moving groups to make a more precise definition of the members of the groups that we already know. And if you can assign a membership of a star to the group, you can extrapolate the age of the group to that star. So that technique is extremely useful. And one way that I've been using that is to get ages for famous M dwarfs, I like to call them. So this, for example, is UV and BL Ceti. These are M6 and M5.5, so it's like a 0.1 solar mass. They are very active. They are flaring a lot. So for those of you that you don't know, there used to be a class of stars called UV Ceti, referring to these stars that are flaring a lot. And it's because of these stars. So there is a lot of information. It's been studied quite a lot. And we still don't, it looks like young, but we don't really know its age. So what I did was to look if that group of stars, that pair of stars belongs to a moving group. And it seems to be, I'm working on this with Leslie Moranta, that she's finding a lot of new moving groups using Gaia kinematics. And UV and BL Ceti seem to belong to one of the groups that she found. according to its position, 3D position, and 3D velocity. And what we can do is go and measure the rotation periods of all of those members and try to estimate an age according to what that sequence looks like. So this is rotation period as a function of color. And to compare it, I'm showing Pleiades in blue, that is 112 million years, and Persepi, that is 650 million years. And in black, you can see the members of the group, of this new group that Leslie found. And down here are UV and BL Ceti. So if we just plot them in this graph, it's very hard to distinguish that they are part of this moving group. They are part of this waterfall of late type M's. But if we, given that we assign the membership of this group, of these stars to this group, we can see that there's a clear sequence in the rotation period versus color plot, and that we can give it an age of around 120 million years, though we are still making those calculations. But as you can see, it lives very close to the Pleiades, so it actually makes a lot of sense. So we can use this technique to measure ages for a lot of famous stars. These are some of the ones that I'm working on. If you have a famous M dwarf that you would like to add, please let me know. But these are some that I'm looking at. There's, again, a lot of information on these stars. For example, well, a lot of coverage in different wavelengths and magnetic field complexity. That is something that we're working on with Cecilia Garrafo here as well. The other way that we can estimate ages using companions is with a comover star, that, like I mentioned before. For this, I developed a code that is called W-dwarf date that calculates ages of white dwarfs from an effective temperature and a surface gravity. So what it does very quickly is from the effective temperature and the surface gravity, using cooling models, it gets the mass and the cooling age of the white dwarf. These are very well-defined models. From the mass of the white dwarf, using initial to final mass relations that are empirically calibrated, we can get the mass of the main sequence stars that generated that white dwarf, and from there get the time that that star spent on the main sequence. If we add the main sequence age to the cooling age, we can get the total age of the star. So what the code does is puts all of this in a Bayesian framework and gets the probability distributions to each of the parameters that I just mentioned, included the total age. So I can use this with systems that are a white dwarf and an M dwarf comovers to get the age of the M dwarf, getting the age of the white dwarf. And using a technique like that, I calibrated the relation between H alpha and H. H alpha for M dwarfs is a magnetic activity indicator. It's not for higher mass stars. H alpha is in absorption for higher masses. Once you go into the M dwarf regimes, it goes into emission, and it's a magnetic activity indicator. It's coming from the chromosphere. The magnetic field is hitting the chromosphere, and that it emits in H alpha. And we can use that as a magnetic activity indicator. So this is an update to a work that I did in 2021, but now we have more white dwarf, M dwarf pairs. So everything that is younger than 1 gigayear is an M dwarf that belongs to a moving group. This is H alpha, a fractional H alpha luminosity on the y-axis and age on the x-axis. And everything above 1 gigayear is an M dwarf co-moving with a white dwarf. The older part of this relation is less constrained than the moving group part because of there are a lot less stars on this side. But this is something that I'm working on to get more H alpha measurements for the M dwarfs that have an age. The sample that I have of M dwarf wire dwarf pairs is like more than 2,000 stars, so we have a bunch. So we just need the H alpha. So now and more famous stars, that's TRAPPIST-1, that falls very well in the relation. TRAPPIST-1 is an M8. So what we can do now, this is something that I'm working on as well, is combine the two to get a more precise age. Each of these parameters work well in different regimes. So combining the two can allow us to estimate better ages. So I can combine the H alpha with, for example, the vertical velocity, and then the color magnitude, the position in the color magnitude diagram. That basically means it depends on mass as well. and combine all that into a likelihood with the models of how the physics works in the low mass stars and get a age probability distribution for each of the stars, combining the two models. Almost done? So the idea is that if we combine the two, you can see this goes from a younger age to an older age. Combining the two improves the estimation for the young ones because H alpha is saying something, but when we get to the old regime is mostly the kinematics that is giving the main constraint because the stars become inactive as they get older. This is simulated data, but next step is going into the data. So that's it. Thank you very much, and I'll take your questions.
So, Rocio, could you also evaluate the lifespan of those M-dwarfs based on their properties? Because obviously many of them could live for 10 trillion years. They would stick around for a while after the sun dies. It's just interesting to see what the age distribution, what the lifespan is as well.
Do you mean what they expect to live, or
yes, how long they expect to live?
Oh, how long they expect? I don't know if we can get that. That's interesting. I always assume that from the models. Like I get if you have the mass.
If you have your parameters, you can. It would be nice to see what is the.
See if they agree.
In the distant future, how the Milky Way would look like.
See if they agree. I never thought about doing it with data, but yeah, that could be an interesting question. But I don't know how you get to trillion years.
Well, your paper will decide it in a trillion years.
Maybe. Hopefully we'll keep getting cited, so that it accumulates a lot of citations, yes.
Any comments, questions? Yes?
So for the age velocity dispersion relationship to get ages indoors, as you go to older ages in larger volumes, you might get contributions from mergers of galaxies and things like that, like GSE, for instance. Have people looked at the contamination rate and how that influences the predictions that you get for ages for M-dwarfs because of these mergers?
Interesting. So for M-dwarfs, that's not something I'm worried about. These are faint stars, so we're not getting very far to get to the place where it would be contaminated by a merger of another galaxy. For giants that you can get farther away, I don't know if anyone saw a difference because of kinematics. I know, not in the age-velocity relation, but at least for the work that I'm doing, is not a problem.
Any other comments? If not, I wanted to invite everyone to stay around. There will be cookies and champagne, and we'll recognize some of the people who contributed to the success of this academic year. Thank you.
Thank you.